Welcome all, my name is Jack Jorgensen. I'm a PhD student in the Department of Mechanical Engineering at the University of Western Australia. Today, for the System Health Lab YouTube channel, I'm going to spend some time introducing the digital twin paradigm and the potential for improved predictive capability through data assimilation. I'll cover this topic from an engineering perspective, touching on the use of simulation models in relation to traditional engineering design and operation workflows, and touch upon the extension offered through digital twins. My hope is that this short presentation will provide some transparency on a concept that can be somewhat contentious and draw attention to the potential benefits available to engineers through considered application of the digital twin. As engineers, we develop components or systems, hereby broadly referred to as equipment, for some useful end. We look to scientific explanation of the physical processes underlying that equipment to optimize the design and development. Commonly, this includes the application of first principles physics-based mathematical models used to describe the behavior of the equipment. In modern-day engineering, the fidelity of such models can vary from simplified and idealized versions solved analytically to ever more complex high-fidelity models involving intractable mathematical expressions that are simulated numerically through compute resources. This application of scientific knowledge in design practice informs our quantitative decision-making and qualitative engineering judgment when faced with complex design and operational choices. We then hand over our design to some end user, potentially another engineer, who uses the equipment in some operational context per their needs. During operation, the equipment is monitored, collecting diverse data sets. These data provide information on state and condition of the equipment and are used to drive performance optimization, improve maintenance decisions, and maximize user value from the use of the equipment. In the traditional application of the engineering workflow, the utility of our physics-based mathematical models of the underlying physical process is concentrated, albeit not exclusively, in the design phase. Simulation of physics-based models do find use in the operational context. However, this generally finds the form of static models, not necessarily updated to reflect the reality of the equipment observed in the data. If we could leverage our observed data in such a way that it could be used to update and improve our physics-based models of the underlying physical process in or near real time, we would expose improved predictive capability. This necessitates a thought process where we see data not only as an indication of state and condition of equipment, but also as a predictor on whether our knowledge of the underlying physical process is correct. A new paradigm emerging in recent years attempts to address this challenge. The digital twin looks to extend the utility of simulation models from being principally a design tool to a whole-of-life predictive tool useful in a real-time operational context. A formal definition of the digital twin, suggested by NASA, positions the term directly in the simulation context. An integrated, multi-physics, multi-scale simulation of a vehicle or system that uses the best available physical models, sensor updates, fleet history, etc. to mirror the life of its corresponding flying twin. This definition reflects that we seek to adapt our understanding of state, condition, and underlying physical process to a particular instance of equipment, thereby exposing the prospect of targeted prediction and decision-making for that particular instance of equipment. This is the core principle of the digital twin, where targeted predictive capability is desired. This necessitates the assimilation of the data with the physics-based simulation models to facilitate a continuous update loop as shown here and adapted from reference 2. The simulation model in green is conditioned on our observed data for a particular instance of equipment in orange. Predictions drawn from this updated simulation model drive operational action, in turn influencing physical operations. This is characterized in reference to as the twinning of the virtual and physical processes. The digital twin paradigm is not dissimilar to traditional engineering process control, where continual monitoring drives operational decision-making. However, unlike process control, Here we seek also to question our understanding of the underlying physical process when we update our simulation models. We adjust not only state and condition, but also the physics-based model itself to most accurately reflect the data observed from the particular instance of physical equipment. We revisit the depiction of the engineering workflow with the addition of the update and predict actions enabled through the use of a digital twin. Scientific knowledge of the underlying physical process is assimilated with observed data, improving the predictive capability of the physics-based model in the operational context to a particular instance of equipment. Activity and progress is noted in some industrial applications for digital twins, including aerospace, energy, and transport. This progress provides impetus for industry to understand the overarching concept and to engage practitioners with necessary skills. The digital twin requires many skills already being developed in the industrial uptake of data science as a vital workforce component for modern engineering practice. In general, these skills require a strong mathematical and statistical basis. Furthermore, skills in computer science for the execution of complex computer simulations and data acquisition, realizing physical observations, are critical. At the intersection of these skills lies the domain expert, the engineer, within whose domain the equipment sits. There is a need for engineers knowledgeable in their respective practice area and conversant in or familiar with all of the above skills to fully realize digital twin value. Converse to the data is all viewpoint that sometimes prevails in discussions on future directions for engineering, the digital twin retains and reinforces the need for subject matter expertise on the underlying physical process. We note the term data-centric engineering is gaining traction within academia and industry, particularly in the UK. Engineers are well placed to leverage data to value through assimilating this data with our understanding of physical first principles. If considered thought and suitable expertise are applied, the digital twin paradigm holds promise for advances to the engineering workflow. Thanks for watching. I hope you enjoyed the video. A short list of references and attributions are shown. Please check out the System Health Lab website for more info and interesting videos.